Can you see the screen?
Yep.
Okay, eigenvalue, right? Good. So we're going to talk about this new section 5.4, the eigenvalue method for homogeneous system. So for those of you who've already taken the linear algebra, you know what the eigenvalue is, right? And, oh, God, hold on a minute. I don't mean that. So eigenvalue is associated with eigenvector, okay? And in the linear algebra, we didn't talk too much about its application. And differential equation, you can see its application over here, okay? It can be used to solve system of differential equations. So in order to understand that method, first of all, we need to know what's eigenvalue and eigenvector. For some of you, this would just be a quick review, but for some of you guys, this would be new. Okay. So first of all, let's take a look at the definition for eigenvalue and eigenvector. Eigenvector. The definition basically is if A is a n by n matrix. Let me see, where's mine? Okay. Ooh. So A is n by n matrix, square matrix, then the solution lambda to this equation, okay, A minus lambda i's identity n, and then with absolute value sign to the both sides. What does that mean in for matrix when you have two straight lines to the left and to the right? You guys recall?
Determinant.
Determinant, yeah. So this is determinant of A minus lambda i's of n equals 0. If you can find a solution to this equation, then those solutions are called eigenvalues. Okay, eigenvalues.
Mm-hmm.
The equation for this determinant equals 0. This equation in algebraic form is also called, what equation is that? What equation is that? Yeah, characteristic. Characteristic. So there are a bunch of characteristic equations in this course. The characteristic equation for looking for the eigenvalues is based on determinant of A minus lambda i's of n equals 0. Eigenvalue lambda sometimes could be 0. So lambda, okay, you may see 0 as eigenvalue. That's totally fine. That's for eigenvalue. Next, we have eigenvector. Okay. Eigenvector is always associated with eigenvalue. So they come as a pair. Okay, you have to specify this eigenvalue is related to this particular lambda. Okay. And the eigenvector basically is the solution of this V, okay, vector V, such that matrix A times V is the same as the scalar lambda times V. So the benefits of having eigenvalue and eigenvector is the matrix multiplication turns out to be a scalar multiplication of a column vector, which is pretty easy to conduct, right? You guys recall, if you do matrix multiplication, you have to do multiplication and summation. However, if you just do scalar multiplication, you'll just need to distribute the lambda to each individual component of that vector V, right?
Yeah.
Mm-hmm. So the eigenvalue and eigenvector has this this benefit. This equation could be moved, okay, can be changed to look. Turns out to be A minus lambda I times vector V equals 0. Okay.
But
This is
my apartment.
how you find, okay, eigenvector V, right? All right, so there are a few notes. First of all, as we mentioned, eigenvector is always related to a specific eigenvalue. Okay, they need to be specified which eigenvalue your eigenvector is related to. Secondly, the vector V here, which is eigenvector, can never be 0 vector. Okay, so we don't have 0 eigenvector, but we do have 0 eigenvalue. 0 eigenvalue is quite common, actually. Next, what is the size of eigenvector V?
N by n. Oh wait, no.
1 by
n.
1 by n by 1.
Yeah, so this is a column vector, right? So it's like has n rows and then 1 column. So it's n by 1. size of those eigenvectors n by 1. Okay, matrix A is n by n. Okay, so we talked about eigenvalue and eigenvector. Eigenvalue basically is the solution to this equation, and eigenvector is the solution to this equation, right? Well, all right, so let's first look at our example 1. Let matrix A be 1, 2, 2, 1, finds the eigenvalues and eigenvectors associated with the eigenvalues. So we have two questions. First of all, find eigenvalues. Secondly, find eigenvectors related to those eigenvalues. Okay. Solution. First of all, for eigenvalue, right? What do we need to do first?
Don't we make it like or lambda minus 1, keep the other two the same, and then the bottom right corner it's like lambda minus 1 again?
Lambda minus, you're talking about the A minus lambda i's of n?
Yeah, I thought, I think
Yeah.
I forget exactly the formula.
Yeah, we have that kind of like a pattern. Let's just start, let's just follow this definition, okay? So it's determinant, okay, would be determinant of A minus lambda i's of n equals 0, okay? Here, A is, let's just do A minus lambda i's of n. And here, A is 2 by 2, right? 2 by 2. So this identity should be size 2 by 2 as well. So A minus lambda times i's of 2 would be 1, 2, 2, 1 minus lambda times identity of size 2. So it's 1, 1, 0, 0. Right, that's A minus lambda I2.
Yeah.
So we have basically the first component would be 1 minus lambda, right? 1 minus lambda. Second entry would be 2. Third entry here would be 2. Last entry will be 1 minus lambda.
But I don't know.
You guys have that?
Yeah.
Okay. So then we're going to set the determinant, okay, determinant of A minus lambda I, which is the determinant of this 2 by 2 matrix. 1 minus lambda 2, 2, 1 minus lambda equals 0, right?
And isn't determinant AD minus BC?
Correct. So in this 2 by 2 case, you just have to do cross multiply. So it's going to be the main diagonal and subtract the other two, right? Which is AD minus BC, A, B, C, D. So we keep going. We have 1 minus lambda times 1 minus lambda minus 2 times 2 should equal to 0. Okay. You guys follow me?
Yep.
Okay, let's simplify this 1 minus lambda times 1 minus lambda. That's gonna be foiling out. So you just have 1 minus 2 lambda plus lambda squared minus 4 equals 0, right? Which goes on saying this is lambda squared minus 2 lambda and 1 minus 4, that is subtract 3 equals 0. This is the equation that has been simplified, which is the characteristic equation. Okay. The characteristic equation is the equation of polynomial using variable lambda. Okay, the next step is pretty straightforward, right? You just go ahead and solve this equation, and we can obviously factor the left-hand side as lambda lambda. For negative 3, we can factor that as minus 3 and plus 1. Therefore, we should have two eigenvalues. One is 3, one is -1. So we have eigenvalue 1 is 3, eigenvalue 2 is -1. Any questions, folks?
No, all good.
Okay, you probably remember this one here. Okay, let's see here. You probably haven't remembered this. When you do A minus lambda I, basically, it's going to be the matrix A, right? Start with matrix A, and then you subtract lambda from the main diagonal entries. That gets you the two eigenvalues. Over next, we go look for the eigenvectors related to these two eigenvalues. Okay, so I'm going to keep going. Oh, sorry. All right. So first of all, let's do eigenvector associated with lambda 1 equals 3. So we're gonna work on the eigenvectors related to eigenvalue being 3. Okay, so those eigenvectors are called x, right? Typically, we call them to be x vector. Is that x vector that we put over there? Oh, v, my bad. V. Okay, so let's call them v, just to be consistent to what we had before. So those v are the solution of this equation, a minus lambda I, v equals 0 vector. Okay. So we should keep going. We say a minus lambda I times v equals 0. And here the lambda would be 3, right? So you can just say lambda 1, okay? And I'm going to replace the lambda by 3. So we have a minus 3I times v equals 0. Okay, the left-hand side, we have a matrix times vector v equals to 0 vector, right? 0 vector. This matrix would be A minus 3I. Okay, so A, matrix A, subtract 3 times identity. And a quick way we'll just be looking at this here. Okay, you guys can just look at this because this is A minus lambda I, right? So we can just plug your positive 3 into here. Do you guys see that? Mm-hmm. You can just use this and simply plug 3 into it. So we're going to get -2, +2, 2, -2. Okay. Therefore, we have -2, 2, 2, -2. V equals 0, right? And this is vector v, okay, should be 2 by 1. Because matrix A is 2 by 2. So vector v should have 2 components. Let's call them just A, B. Okay. So we're going to go ahead and have -2, 2, 2, -2 times this column vector of A, B equals to 0 vector. So it should be 0, 0. All right.
Mm-hmm.
Yes.
Okay, next, let's go ahead and multiply the left-hand side. So this is multiplication. Let's just do the multiply by using the matrix multiplication rule. So you're going to have first row times first column for the first entry, right? So basically that gives you -2a plus 2b should equal to the first entry 0. That's good.
Yep.
Yeah, second row, you pretty much have the similar. So you have the second row times the only column. So we have 2a minus 2b should equal to the second entry, which is 0. In fact, if you look at these two equations, aren't they the same?
Yeah.
Right?
Yep.
Because they're the same equation. If you just do a simple simplification, that's the same, telling you matrix the A minus B should equal 0, which means A should equal to B, right? Good so far?
Yeah.
Yep.
Yep.
Yeah.
Okay, so I can just say, okay. I'm having trouble seeing my pen. Oh, there. So the eigenvector corresponding to, so for lambda equals 3, eigenvector v will just be a, b, which is the same as a, right? And you can pull out the a, because a is just a scalar. Basically, it's just going to be a vector 1, 1. That's right, Ricardas?
Yep.
So these eigenvectors, they are all the scalar multiple of the vector 1, 1. Okay, scalar multiple of vector 1, 1. So I can just take out the vector 1, 1 for the general representation of the eigenvector for lambda equal 3. Okay, does this ring a bell?
Yeah.
Yep, to what you learned in linear algebra, right?
Took a minute to come back, but yeah.
But remember these process, right? The same process. Okay, so we just did the eigenvectors corresponding to lambda equals 3. So similarly, let's do the eigenvector associated with lambda equals -1. All right, let me see. So item 3, I'm gonna go eigenvector associated with lambda 2 equals -1. So same thing, it comes from a minus lambda I times vector v equals to 0 vector. And we have said the quick way to get this coefficient matrix, right? A minus lambda I. What's the quick way, folks?
Just plugging it in.
Yeah, just plug this into here, right? Plug here. 1 minus lambda, 2, 2, 1 minus lambda. Here, lambda is -1. When you plug -1 in, I have 2. So 2, 2, 2, 2. Vector v, let's call it to be CD, to be different from AB. And it equals to 0 vector, which is 0, 0. Okay, then let's perform the matrix multiplication again. You have 2, 2 times CD. That gets you 2C plus 2D equals 0, right? Equals the first entry. The second row basically gives you the same equation. So 2C plus 2D equals 0. What does that tell us about C and D?
They're equal to the negative of each other.
Yeah, so C equals -D, right? Or D equals -C. They're opposite of each other. So I can say the vector v in this case will just be C, D. Okay, D would be -C. I'm just saying D would be -C. If you pull out the C, it will just be 1, -1 as the representative eigenvector. Okay. Let me just pull out here. And all of these are eigenvector associated with lambda equals to -1, right? Is that good?
Yeah, good.
All right. In the end, let me just do a very quick summary of this question. Okay. So for this matrix A, we've got lambda 1 equals to 3 and lambda 2 equals to -1, right? 2 eigenvalues. For the eigenvector related to lambda equals 3, I can say it's 1, 1 as a representative. For eigenvector corresponding to -1, I can say the eigenvector would be 1, -1. Okay? These are the representative eigenvector. And of course, you can multiply this eigenvector by any scalar like other than 0, right? To get a bunch of others. Any problems so far?
No, all good.
So question.
Martin, yes.
If we would get an eigenvalue, which is not possible of 0,
Eigenvalue.
is that even possible? What did we
Are you talking about eigenvalue or eigenvector?
At the bottom it said it can't be 0. At the top, sorry, at the top. In
Okay.
the rules.
Okay, eigenvector cannot be 0 vector, but eigenvalue can be 0.
Okay.
Right? Mm-hmm.
If we would get that equal to 0, is that just not possible in the calculation, or did we?
Are you referring to eigenvector or eigenvalue?
Eigenvector.
Eigenvector can never be 0. So
we
you gotta
must have
check
made a
your
mistake.
computation. Yeah. You must have some A and a B. There has to be some relationship between A and B, so they can never be 0. Mm-hmm.
Professor, could one of those A or B be 0?
Oh, absolutely. If one of them is 0, that's fine, as long as they're not all of 0. That's considered to be a non-zero vector.
Okay, got it. Thank you.
When I say 0 vector, it's referring to all the entries being 0, right? Martin, has that answered your question?
Yes, thank you.
Great. Okay. So that's a very quick review or introduction of what's eigenvalue and how do you find eigenvector. Next, let's talk about how do we actually use the eigenvalue to solve for homogeneous system. So again, here we're emphasizing this is for homogeneous system. Okay, homogeneous system. So we have a theorem here, eigenvalue solutions of homogeneous system. Let the unknown vector be x. So suppose we have like n unknowns, x1, x2, x of n. And we have a homogeneous first order equation system. So it's first order x prime equals matrix A times x. Being homogeneous, there's nothing else being added. Okay, only x prime equals A times x. This is a first order homogeneous linear system we're looking at. So if lambda is an eigenvalue of A and V is its associated eigenvector, then the theorem says I can get a vector which is x. I can get a solution. The solution is x equals this V, the eigenvector times e raised to the lambda t. Okay, so this x equals v e raised to lambda t would be a non-zero solution to this system. Okay, let's name the system. over here. So suppose this is system star, then this x equals eigenvector times e raised to eigenvalue times t would be the non-zero solution to the system star. Okay. So this is the first theorem, theorem 1. It talks about how you can get a non-zero solution to the system by using eigenvalue and a corresponding eigenvector. Okay, so now the question is, when you guys think about eigenvalue, right? Lambda be eigenvalue of matrix A. The matrix A may have multiple eigenvalues, right? Folks, would you agree?
Yeah.
Yeah.
Like the example 1 we did, okay, example 1 we did, there are 2 different eigenvalues and they're both real numbers, right? Okay. So based on different cases of those real eigenvalues, we would be looking at 2 different cases. The first case would be, what if the matrix A has distinct real eigenvalues? Second case is, what if it has conjugate complex eigenvalues? So real eigenvalues versus complex eigenvalues. First case, we have matrix of distinct real eigenvalues. We can use the eigenvalue method in this case. So again, there is another theorem. This theorem actually has been introduced in linear algebra. If you recall, in linear algebra, we did talk about this. So the theorem 2 says, eigenvectors of different eigenvalues, they are linearly independent, okay? So if I have 2 different eigenvalues, say lambda 1 is different from lambda 2, then their eigenvectors v1 and v2 would be linearly independent, okay? When do we need this linear independency, guys?
When our solutions aren't the same.
Linear independency is especially used for when you're looking for, remember, general solution, right? General solution. You need to guarantee those, you need to make sure those individual solutions are linearly independent. Okay, independent. So let's see, in this case 1, if you have matrix of distinct real eigenvalues, how do we find their general solution? So this is the method for case 1. I'll give you guys a few minutes to read through it. Okay, does that make sense to you? So basically what they're doing is they're solving this matrix A and then getting eigenvalues, right? And we assume these eigenvalues are different. So lambda I is different from lambda j if I is different from j. They're all distinct eigenvalues. If they're all distinct eigenvalues, then v1, v2, v sub n, all of these are linearly independent, okay, independent. And using v1, v2, v sub n, as well as the lambda 1, lambda 2, lambda n, you can construct these individual solutions to the system. And due to the linear independency of v1, v2, v sub n, all of these would be linearly independent. Yes, so we have n linearly independent solutions to the system star, right? To the system star. So can we fill in this answer? Then the general solution to the homogeneous system star would be what?
Linear combination of
Correct.
those x1,
x1,
x2,
x2, x.
and
So x will just be c1 x1 plus c2 x2 plus da 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 plus cn x of n. And each x1, x2, x of n is constructed by eigenvector and its eigenvalue, right? So x1 here is v1 e raised to lambda 1t, and x2 here is v2 e raised to lambda 2t, and you keep adding until you get the last solution, cn, vn e raised to lambda n t. Is that clear, folks?
Once we practice it, it'll probably make more sense.
Yes, we will have enough chance to practice. Okay, so basically what you need to do for this method is, first of all, you find all the eigenvalues, and then you find all their eigenvectors, and then construct x1, x2, x of n. In the end, you just get a linear combination of these individual solutions. It's not difficult when we actually put it into the context of the questions. Okay.
So I have one question.
Sure.
x1, x2, xn, are those column vectors?
Yes, they're column vectors because they would be solutions to the system. So they would be containing like n components.
Yeah.
Mm-hmm.
So they're basically kind of eigenvectors.
They look similar to eigenvectors. They have the same size, right?
Yeah.
Okay, we'll see that in actual problem. How's that?
Yeah, perfect.
So example 2, solve the system by eigenvalue method. Okay. All right, first of all, let's rewrite this into matrix equation. Where's my pen? Here, pen. All right. Let our unknown x to be containing 2 entries, x1, x2. And let our matrix A, coefficient matrix A, be what?
1, 2.
1, 2, 2, 1. Right? Does this look familiar? 1, 2, 2, 1.
Mm-hmm.
Don't we just look for its eigenvalue and eigenvectors?
Oh yeah.
Right? Yeah, that's why I do that here. Okay. So once you see that, we can say the system will just be equivalent to be vector x prime equals to a x, right? You can see x prime equals a x. Make sense?
Yeah.
Yeah.
Is this homogeneous?
Mm-hmm.
Homogeneous, and it's first order, right? First order system of differential equation. So we can use eigenvalue method to solve for x. Good.
Mm-hmm.
Let's see how we do that. So we've said for matrix A, we've got 2 eigenvalues, lambda 1 and lambda 2. Is lambda 1 3 and lambda 2 negative 1?
Yeah.
And their eigenvectors, let's just call this to be v1 and v2. Previously we just called them v and v, but now let's just put a subscript here, 1 and 2, to match the lambda. Okay. Did we have
1, 1.
1, 1,
1, negative 1.
1, negative 1 for these 2 eigenvalues, right? Alrighty. So once we have lambda 1, v1, lambda 2, v2, we can construct two solutions. Okay, we can construct solution x1, okay, first solution, and second solution x2. The x1 would just be v1 times e raised to lambda 1t, and x2 would be v2 e raised to lambda 2t. I'm running out of space there, so I'm gonna just continue here. So first solution is v1, 1 times e raised to the 3t, right?
Yep.
Okay, you can multiply e to the 3t into these two components. So you have e to the 3t, e to the 3t. And x2 here would be v2. So eigenvector 2, 1, negative 1, times e raised to the lambda 2t, so negative t. Is that easy?
Yep.
So let's just multiply e to the negative t. We have e to the negative t, negative e to the negative t. Okay. So x1, x2 has been constructed. Okay. And what are these two, guys? What are these two?
There are solutions that we need to add up.
Yeah, they themselves, right? They themselves individually, they are a solution to the system. Okay, they're both solutions to the system, and more importantly, they are linearly independent, right? So these are linearly independent solutions to my system x prime equals ax. Okay, so are we ready to write down the general solution?
Yeah.
Yeah.
So the general solution to the system x prime equals ax is, I can call general solution bx, would just be a linear combination of these two, right? So c1 x1 plus c2 x2. You can go ahead, c1 x1, so e to the 3t, e to the 3t plus c2 x2, so e to the negative t, negative e to the negative t. So eventually, if you want to write them out, okay, this is c1 e to the 3t plus c2 e to the negative t, and c1 e to the 3t minus c2 e to the negative t. Is that good?
Mm-hmm.
Yep.
Okay, what do these numbers represent, by the way? What do this and this represent? They are the actual unknowns, right? So the unknown is actually x1, x2. So they are the specific x1 and the specific x2 in the original system. Is that clear? Questions before we move on to the next problem? Any questions, folks?
So you're never going to plug in the x1 and x2 into the equation, x1 plus 2x2, or the other one below it? You get what I'm saying?
No, Philip.
Um,
Which equation are you referring to?
Like the one at the very top, the one that's
system?
already written.
This one?
Yeah, that. Are you ever going to plug in what we have for x1 and x2 into the actual
You don't
equation?
have to. I mean, if you want to verify, right? If you want to verify your answer is correct, you can put the C1 e to 3t plus C2 e to negative t into the system equation for x1, and the other one into the system for x2. If you
Okay.
want it for verification purpose, yeah.
Okay.
But other than that, you don't have to do that. Unless you want to verify your answer is correct. Okay? Any other questions, folks? All right, if not, then we're going to continue to the next page. I have example 3, solve the system by eigenvalue method. Okay, so we're going to do this again. This time we don't have the eigenvalues set up yet, so we're going to start off from the scratch here. Let me see, I want to make sure I have enough space here on this page. All right, so I'm going to do here, I'm going to use this every individual space, so solution.
Hi, sorry, my internet went out.
Okay, first of all, let us have the unknown vector x. How many unknowns are there?
3.
3, so x1, x2, x3. And matrix A would be
4, 1, 4.
4, 1, 4. Yeah, just to read their coefficients, right? So 4, 1, 4, 1, 7, 1, and then 4, 1, 4 again. 4, 1, 4. Then we have the system, will just be x prime equals ax. Again, this is homogeneous, and this is first order, right? So we can use eigenvalue method, okay, to solve the system. Okay, eigenvalue method, we have first of all solve for the eigenvalue, right? So, so first, let's find eigenvalues of matrix A. So we need to have, let's determinant of A minus lambda I equals to 0, right? Determinant. What's the size of identity in this case, folks?
3 by 3.
So I3, because matrix A 3 by 3, right? All right, so we are just gonna do this. Let me see, I'm gonna move on to here. The determinant equals 0. I'm just gonna go straight. Okay, so we know the shortcut already, right? So 4, 1, 4, 1, 7, 1, 4, 1, 4. And we're going to subtract lambda from all the main diagonal entries. So minus lambda, minus lambda, minus lambda for those 3 entries. Is that correct?
Yeah.
Okay, now I'm going to leave it to you, and you guys figure out this characteristic equation. Remember, we talked about a 3 by 3 matrix, right? You can do the arrow method if you want to for the determinant.
What's it called when you do it by a row or column and you
Cofactor expansion?
Yeah, that.
Sure. If you remember cofactor expansion, you can do cofactor expansion as well. Use the one that you like the most.
I remember. I just feel like I'll do it wrong.
Cofactor expansion, yeah. Let me just do the difficult one here, which is the arrow method. So I'm going to do 4 minus lambda, 1, 4, 1, 7 minus lambda, 1, because not everyone has taken linear algebra. So 4, 1, 4 minus lambda. And I'm going to copy the first column and second column here, right? So 4 minus lambda, 1, 4, 1, 7 minus lambda, 1. Did I copy everything correct?
Yeah.
Okay, and I'm gonna do the big work here. Okay, so I'm gonna do rightward multiplication. So this arrow, and this arrow. First of all, right? Okay, so I have 4 minus lambda times 4 minus lambda. So that's 4 minus lambda squared times 7 minus lambda plus 1, 1, 4, which is 4, and plus 4, 1, 1, that's 4. That's the right word. And next we're gonna do leftward. You guys recall? These, and these. I hope you can still see my screen. So it's minus 16, 7 minus lambda, minus 4 minus lambda, minus 4 minus lambda. Okay, the whole thing should equal to 0. Right? All right, next I'm gonna give you guys a few minutes. Expand everything. Let's expand everything and combine the like terms. What can you guys get?
Can I ask you a quick question on cofactor expansion?
Sure, Philip.
So I kind of remember if you did like the first column, for example, and then when you do the 4 minus lambda, you would cut out the top row and just do the determinant of the 2 by 2.
Correct. So
And
if
then
it's
what, you
4
multiply
minus
that
lambda, you're gonna look at the determinant of this, right?
times 4 minus lambda, right?
And then you
Correct.
can multiply it
And
by the
plus-
-1.
Plus the 1 times whatever, plus the 4 times whatever.
Okay, the trick when you're using the cofactor expansion is if the first one is plus sign, the second one would be
Oh, yeah,
negative
yeah.
minus sign, and then the plus sign, right?
I remember
the checkboard pattern of the signs, right?
Uh-huh.
That's the only trick you have to pay attention to.
Okay, so you would subtract the 1 and then plus the 4 times whatever and add it
Correct.
together and you
Yes,
have your answer.
that is correct. Other than that, you know the method.
Okay, thank you.
No problem. The rest of you guys, please go ahead and simplify this polynomial. Okay, has anyone got the polynomial? What's the coefficient for lambda? Oh, first of all, do we have lambda cube?
Yeah, -1,
Okay, negative lambda cube. What's the coefficient for lambda square?
+7.
Is it positive 7? Other numbers? Folks, other numbers?
Oh, I got 1. No,
One?
-1.
A negative 1?
I see.
Lambda square.
Other numbers? Folks, other coefficient of lambda square you guys got?
Just 1.
Nope.
Maybe -1.
-1.
Nope. I
No.
don't get anything. I get 15.
What?
Do you have 15?
Ah, yes, yes, yes.
15, right? Good.
Yes.
Oh, I forgot my negatives. Yep.
Great. What's the coefficient for lambda?
-51.
51? That's a weird number. 50.
I got negative 66.
56? Close.
Is it 66?
50 something? Yeah, what is that? 50. Did anyone get 54? Negative 54.
Yeah.
Okay, good. The negative 54 lambda. Was that Joshua?
Yeah.
Okay, yeah.
That was me.
Good. So if you did everything correct mathematically, you should have negative lambda cube plus 15 lambda square minus 54 lambda equals 0. You can call this the characteristic equation, right? Characteristic equation. But anyway, you guys are close. There is no constant because the constant happens to be all canceled out. Okay. Of course, you don't have to write this. You can change its look to lambda cube minus 15 lambda square plus 54 lambda equals 0. And then we're going to go ahead and solve for lambda. Right, solve for lambda. Obviously, what can we do first of all?
Pull out 1 lambda.
Pull out lambda, and then we would have lambda square minus 15 lambda plus 54 equals 0. Right? Is that factorable?
Yeah. Wait.
What, Eric?
No, I don't even know. I thought I couldn't read what number it was again. My bad.
54.
Okay, not a negative.
6 and 9, right? So we can do lambda minus 6 and lambda minus 9, both negative and equal 0. All right, so we have 3 lambdas. Lambda 1 equals 0. Martin? Martin?
Yes.
This is the case, lambda equals 0. Right?
Thank you.
No problem. And then second, lambda 2 would be 6. And lambda 3 would be 9. So there are 3 distinct real eigenvalues. Okay. So let me put it here. Where's my pen? The I'm looking for. Oh, gosh. Oh, here. Okay. So distinct real eigenvalues, which matches our case, right? Distinct real eigenvalues. Okay, so next we need to look for the V1, V2, and V3 for each individual one. Okay, so next look for find eigenvectors. Okay. First of all, for lambda equals 1 equals 0, for the first eigenvalue, we're gonna do A minus lambda I times V equals 0, right? A minus lambda I times V equals 0. Is that good? Basically, it just says it is for my matrix A. Okay, matrix A is 4, 1, 4, 1, 7, 1, 4, 1, 4. So it's 4, 1, 4, 1, 7, 1, 4, 1, 4 times V. This time you can say let V contain 3 elements, A, B, C. Okay, so A, B, C equals to 0 vector. So it should have contain 3 zeros, right? You guys okay? All right. This is a little bit complicated, so we're going to do multiplication 414 times ABC. 4A plus B plus 4C equals 0. Second, I can have 171 times ABC. So A plus 7B plus C equals 0. And lastly, you see the 414 again. So basically, it's the same equation. 4A plus B plus 4C equals 0. This is equation 1. That's equation 2. That's equation 3. However, equation 3 doesn't really, it's not very useful because it repeats equation 1, right? Good?
Yep.
Okay. So you just be looking at equation 1 and 2. If you remember, oh, question? Any
I was
question?
going to say, couldn't you multiply by -4 to cancel out the A and the C and just have B?
Yes, you can do that. So look at equation 1 and 2. I can do equation 2, equation 1 to remain as it is, 4A plus B plus 4C equals 0. Equation 2, let's multiply by -4, right? So you can get -4A minus the -4, so 28B minus 4C equals 0.
So you just skip B.
Okay, so this will be equation 4. This is equation 1. I can add these two equations, 1 plus 4, and A and C all got canceled, right? A and C all get canceled. What do we have? We get -27B equals 0, right? It tells you B would be 0. Has to be 0, right? Good so far?
Yep.
Okay. So we are sure the entry B needs to be 0, and then you can plug into either equation 1 or equation 2. I'm just going to use equation 2 because that's pretty straightforward. So plug into equation 2. I'm having A plus C equals 0, telling you C would be -8, right?
Mm-hmm.
All right, so this V, this vector V, eigenvector, actually you can call this to be V1 because that's corresponding to lambda 1 equals 0, right? So V1 would contain A, B, C theoretically, but we have said B needs to be 0, right? B needs to be 0, and entry C needs to be -8. Good?
Yep.
All right, so easy to see. We can pull out the A and leaving 1, 0, -1. If you remember in linear algebra, this is called the base, right? So the base.
Mm-hmm.
The 1, 0, -1 would be the base of all the eigenvectors. By the way, I don't have to do, but it won't be there. I'm going to say this would be specifically, this would be my V1. Okay, 1, 0, -1. Is that good so far?
Yep.
Okay, I'm going to ask you guys to find the eigenvector for lambda equals to 6 and lambda equals 9. Go ahead.
Could you scroll down just a bit so I can see matrix A? Thank you.
Scroll up. Is this helpful?
Yep.
Okay. Just a little bit more.
I have a quick question.
Sure. What is it, Philip?
Could we do what we did in linear algebra with the matrix and make it solve it equal to 0 with the RREF and get the value for A, B, and C instead of doing it
Sure,
by
absolutely. You can do that. Mm-hmm. Yeah. Use whatever you have learned. Over here, I'm trying to keep it to the simplest because not everyone has taken linear algebra. Mhm. Okay, I'm gonna go ahead and work for the eigenvector when lambda equals to 6. What did you guys get for lambda equals 6? The eigenvector. Anybody?
Nothing yet.
Not yet.
I'm not sure. Is it 1, negative 0?
1, like Eric, what is your second component?
Negative 1?
Is it negative 2 or negative 1?
I might have did the calculations wrong, but it's a negative.
Yes, it's negative. It's 1, some negative number, and 1. Yeah, close. All right, so I'm gonna do it here. So 4. Let's see here. All right, so for lambda 2 equals 6, I'm gonna have a minus lambda I v equals to 0 vector, right? So you should have, so 4 minus lambda, 4 minus 6, that's going to be negative 2, 1, 4, and 1, 7 minus 6, which is 1, 1, 4, 1, and 4 minus 6 will mean negative 2 times A, B, C equals to 0, 0, 0. Okay. All right, so that will give us negative 2A plus B plus 4C equals 0. A plus B plus C equals 0. And 4A plus B minus 2C equals 0. Right, guys?
Yeah.
Okay.
Yep.
If you know linear algebra, absolutely you can do elementary row operations to get it to reduce the row echelon form, and then look out for A, B, C, right? If you don't know about that method, you can still use your previous knowledge in middle school or high school to solve for A, B, C. Over here, I think B is relatively easy to eliminate. You guys agree?
Yes.
Right, so you can use equation 1, 2 to eliminate B, and you can use equation 2, 3 to eliminate B. I can say equation 1 minus equation 2, I'm getting negative 3A plus 3C equals 0. And equation 2 minus equation 3, equation 2 minus equation 3, I get negative 3A plus 3C equals 0. So these two get us the same conclusion, which is A equals to C. Do you have that?
Yep.
Yes.
Right? At least A, C are the same. Okay. If A and C are the same, you can either plug this into equation 1 or equation 2, right? Okay, now plug A equals C into any one of those equations. Oh, maybe equation 2 would be easy. Plug into equation 2. Because it doesn't have all kinds of different kind of coefficients. So I'm going to have A, which is A, plus B plus C. C is now A, right? Equals 0. So that tells us B is negative 2A. Is that good?
Yeah.
All right, so do we know that A, B, C, their relationship?
Yes.
1, negative 2, 1.
So I'm going to say vector V is A, B, C in general, and here all the B and C could be represented by using A, right? So A, B would be negative 2A, and C is same as A. So if I pull out A, I'm having the base, which is 1, negative 2, 1. Does that make sense? Great. So I'm going to call this as my V2.
Do that with like an adjustment layer using W, like an adjustment layer.
So this could be eigenvector for lambda equals to 6.
No different adjustment layer. Like, so is it like no objects moving?
Is there another class going on?
And
Yeah, I'll mute myself.
All right. Lastly, I'm gonna just do. Okay, and then next we're gonna find eigenvector for lambda equals to 9. It's a 9. Okay. What did you guys get for this? Did anyone have a chance to solve for ABC in this case?
Almost.
Okay.
Yeah. Did I get 1, 0, -1?
Great. Okay, so I'm going to save the time here. Yes, so V3 would be 1, 0, -1. You used exactly the same method as we did in these two cases, right? All right, are we almost ready to go ahead and write down our solutions? Okay, am I running out of space on this page? Okay, I'm going to do it here. All right, so basically what we've got lambda 1 equals to 0, lambda 2 equals 6, and lambda 3 equals 9. And V1 for lambda 1 is 1, 1, 1. V2 for lambda 2 is, okay, this is, V2 is 1, -2, 1. And V3, if you got it right, you would have 1, 0, -1. Okay, so I can just say, I'm just gonna go skip some steps, okay? General solution, x of t. How many individual solutions we can get for these 3 eigenvalues?
3.
Yeah, so we can get C1, x1 plus C2, x2 plus C3, x3. Be careful when I say x1 vector, x2 vector, x3 vector, I'm not referring to, this is different from the original x1, x2, x3, okay? This x1 vector, x2 vector, x3 vector are 3 individual solutions to the system, okay, to the system. So I'm going to say each one of those is made up by lambda and a v, lambda and v, and lambda v, right? So x1 would be v1 e raised to the lambda 1t, and x2 would be v2 e raised to the lambda 2t, and x3 would be v3 e raised to the lambda 3t. Okay, so we have C1 times 1, 1, 1 e raised to the 0t plus C2 times 1, -2, 1 e raised to 6t plus C3 times V3, 1, 0, -1 e raised to the 9t. Where's my pen? All right, here. This so far, folks?
Yep.
Yep.
All right, we're almost towards the end. All right, so we're gonna say, let's write down the column vector of 3 entries. Okay, we can just do first entry, all the first entries add them up, and all the second entry add them up, and all the third entry add them up. Remember, e to the 0t, this is the same as
1.
1. Okay, so this is just 1. So we have C1 times 1, which is C1, plus C2 e raised to 6t, plus C3 e raised to 9t. That's the first entry, right?
Yep.
Second entry would be C1 times 1, still is C1. And then the second component here is -2C2 e raised to 6t. Lastly, we have C3 times 0, so that's just 0. All right, the last entry, we have C1, 1, so that's C1, and plus C2 e raised to the 6t, and then subtract minus C3 e raised to the 9t. That's my unknown vector, right? Which means it's referring to the x1, x2, and x3. So here's x1, here's x2, here's the x3 in the original equation. You can also say, let me see, this is equivalent to say the x1, x2, x3. x1 would be c1 plus c2 e to the 6t plus c3 e raised to 9t. x2 is c1 minus 2c2 e to the 6t. x3 would be c1 plus c2 e raised to 6t minus c3 e raised to the 9t. This would be the general solution, right? General solution. All right, any questions? Let me zoom out a little bit so you can get a bigger view of what we just did. Any questions, folks?
Dr. Wu, I have one question which is MATLAB related.
Mm-hmm.
So, for eigenvector using
Yes.
MATLAB.
Mm-hmm.
So, can we solve for coefficients in MATLAB using reduced row echelon form?
Yeah, you can do that. Remember we did an algorithm in MATLAB, right?
Yeah, I mean, I'm trying to, but I was not getting the right results.
We can talk about that after class.
Okay.
How's that?
Yeah,
okay.
perfect.
Mm-hmm. Yeah. So you stay in the meeting, and the other folks,
Okay.
we are ready. We're done.
Thank you.
Okay, so you guys go and have a good weekend. I'm going to assign homework on my courses, so you practice. All right, these problems, sometimes they may be long.
Have a good weekend.
Bye.
Thank
Have a good
you.
weekend.
Bye. And as for Milan, you can share your screen with me if you want to.
Right? Yeah.
Are you in front of your MATLAB?
Yes, I am.
Okay, so you can share your screen with me and let me see what's going on there.
So because you're sharing your screen, I cannot share mine.
Oh, okay, sorry. Let me stop share.
Okay.
That's a good point. Now you can go ahead.
All right.
You can share your screen with me to see what's up there.
Which one do you see?
Oh, yeah, I see it. Okay, I see your
MATLAB?
matrix A, B. Yeah, MATLAB.
Okay.
I see the editor tab.
Yeah, here.
Mm-hmm.
So this is basically 4 minus whatever.
Correct. Mm-hmm. Yeah.
That gives us
Mm-hmm.
the matrix, and then I add solution matrix to the
Okay.
fourth column,
Yeah, you're almost there.
and then reduce your echelon form.
Yeah. Uh-huh. Sure.
This is the function,
Mm-hmm.
but I don't get the. Am I supposed to get in the fourth column the answers, the solutions?
Okay, now you actually have it already there. Okay, remember, yeah, so if you look at the reduced row echelon form equals to this matrix, right?
Yeah.
The left three columns, 1, 0, -1, 0, 1, -1, 0, 0, 0. The left three columns represents the coefficient matrix.
Okay.
And the right-hand side, 0, 0, 0 are just the right-hand side, right?
Yeah.
So if you write, if you convert this into a equation, what do you have for the first row? What does that first row tell you?
So that we have x1 minus x3 to be 0. Or
Okay,
A,
you are looking at eigenvector, right? If you're looking at eigenvector, we're using A, B, C for that, right?
yeah, A minus C.
A minus C equals 0. What does that tell you?
Okay.
So
That
A equals to C, right?
Yeah.
The second row tells you B equals to C.
Yeah.
So A equals B equals to C, which is the one that we had. Our eigenvector is having base 1, 1, 1.
Okay.
See that?
Yeah. So would that be for? So that isn't that for?
Sure, you can change the 9 to other eigenvectors, eigenvalues, right?
Okay, so if it was for lambda 0, oh, sorry.
Mm-hmm. So if you do a 0, just be 414, 171, and 414.
And
Mm-hmm.
it seems like I get different.
No, it's different. It's not different. So once again, if you look at the first row, what does it tell you?
A equals to negative C.
Yes, A equals negative C. What does the second row tell you?
B equals to 0.
Yeah, isn't that consistent with our solution?
Yeah, isn't that lambda 3?
Yeah, that's for lambda 3 equals 0. The eigenvector we picked
Okay.
as 1, 0, negative 1, right?
Yeah, okay, yeah, I had lambda 1, lambda 3 different in my.
Oh, okay.
Yeah,
Yours is
that's
in
why.
different order,
Okay, okay,
but
yeah.
as long as you see the eigenvector corresponding to the eigenvalue, it's the same, right?
Yeah, okay,
You do
makes
have it.
sense.
So this will be a quicker way if you
Yeah.
just do it in MATLAB.
Yeah, that's what I was trying to, but I was confused.
Sure, absolutely. But you're on the right track. Mhm.
All right, perfect. Thank you very much.
No problem.
Thank you.
Okay.
Thank you.
Have a good weekend.
You too. Bye.
Bye. All right, so I'm gonna end meeting, okay?